Fantastic. Take it away. This is so cool. I can't wait to see this.
Thank you. Good evening, everyone. Thanks for turning out and thanks for having us. My name is Malak Siva, and I'm joined here with my two colleagues, John Osbury and Austin Epps. We would like to tell you a little bit about how we, as part of a bigger team, managed to contact a space probe that was launched almost 36 years ago, and the adventure that was. So the actual space probe's acronym is ISEE-3. It was launched as one of 3 probes, and the Reboot project is the sort of name that the team goes by that's contacting the space probe again. So guys, do you want to introduce yourselves quickly? By the way, I like software-defined radio. Who's heard of software-defined radio? Oh, look at that! Wow, cool. That's really neat. So I work at Edis Research. That's where I met John. John used to work there. He's also a bit of an SDR guru, and I met Austin as part of the project. Do you guys want to quickly introduce yourself?
Sure. Pretty quick. My name's John Malsbury. As Bob said, I used to work at Edis Research. Unfortunately, I was a marketing guy at that time, but I have recently departed, and this was a great project to get involved and prove that I could be more than just a marketing guy.
Yeah,
so it's like I don't always write code, but when I do, it talks to a space probe. But it's been a great opportunity since Edis Research. I recently joined a team at a company called NanoSatisfy. And they're in the business of building CubeSats and lots of them and using them to gather various types of data. So, small plug, we are hiring if anybody's interested. Feel free to reach out to me afterwards.
Hi, I'm Austin Epps. My background is in aerospace engineering, so these guys know about a million times more than I do about the specifics of RF, but as far as the operation of spacecraft and that sort of thing. So I have some experience with working with old NASA data. I was on the Lunar Orbiter Recovery Project, which is ongoing. We have all of the data from the 1966 and 1967 mission series Lunar Orbiter, which was 5 missions in the 1960s to map the surface of the moon. We're digitizing all of that with from the original magnetic tape, and that's how I got involved.
Their office is an old McDonald's that they've converted into a place called McMoon's, and I believe that you fly a pirate flag on the window, right? And it's actually quite incredible. I wish I would have had a photo here. You go in, and it seems so recognizable because it's the replicated layout of every single magnet. But you go in, and this is where you normally order your food, but it's all they've got computer equipment on it and stacks of tapes.
Right, so it's the McDonald's at Mott Field, which is when the Navy left, it became NASA Research Center was already there. So NASA took over the operation of the entire thing. So we're in a NASA building which used to be an old McDonald's, and we've been there for 6 years now.
All right, so let's get down to it then. This is an artist rendering of the space probe. It was, where are you going, guys? I'm going to throw it back to you. The International Sun Earth Explorer #3, and it was launched a little while ago. It had a phase to a heliocentric orbit. I'm going to show you what that looks like in a second. And its primary aims were to study the interaction between the solar winds and Earth's magnetic field. You can see that it has all these sort of arms coming out, various antennas and so forth. It was renamed to ICE, so we sort of interchangeably refer to it by both. And it was, it first did a couple of different things. First, spacecraft in the halo orbit at an Earth Sun L1 point, and I'll explain what that is. And it was also the first spacecraft that passed through the tail of a comet. So it's seen some interesting things. So this is what the Lagrange points are called. This was physically with L1, so this is the Sun and this is the Earth. Then this is a special point in the orbit where, as the Earth orbits the Sun, the space probe would actually follow with it. Would you agree, rocket scientists? Is that okay? Yeah. I'm just a radio guy. So if you were to sort of render that out, you have the Sun and the Earth, and you can see at these various dates the different points at which the space probe was. And the incredible thing about this, apparently, and correct me if I'm wrong, but one guy was able to visualize this entire thing in his head and then tell NASA this is when you need to do various burns, this is, you know, when you haven't, so it'll end up here in 30 years. And he mapped it out all these things, like saw in multiple dimensions. It's pretty incredible. But this is sort of the L1 point here where I hung out for a while in that halo orbit. So if I quickly switch over to a web browser, then this is an animation of the, is that, no, it helps if I put it on the actual thing. Maximize. Oh, where'd it go? So you can see here, this is the sun, this is an inertial reference frame, and then the space probe is right there, if we follow the mouse, and it's just about to catch up with the Earth. You see, that's what's actually happening right now. So we're at the point where it's just come around, and it's about to catch up with the Earth. It's actually really close now, and we've been talking to it right there. And so we want to capture it now before it's too late, because if we miss that, then how many more years is it going to be until we see it again?
Depends on how close it passes to the moon, but at least 15.
Okay, so that's why there's a bit of a sense of urgency here. So, what's going on? Firefox has taken over the screen. All right, here we go. So this is an example of a particular projection of the orbits of the Earth and the space probe. You can't actually see it because Ultramon has done something weird. I'm going to turn it off. But if you look closely, this spiral sort of orbit is the space probe, and you can see that comet that it happened to intersect with at a particular point in time. So it's amazing that they were able to plan out the orbit in advance like this and have it all work. And this is a curious frame because unlike the inertial reference frame which is looked at before, this is sort of drawn by having the Earth statically centered at the plot at the bottom and then the sun is off to the left. So you kind of have to imagine this entire reference frame moving as the Earth orbits the sun. And I'll show you what that looks like in a second. But if you were to zoom out, this is the inertial frame.
This is a rotating frame.
Do you want to explain that? I'll pull up the video in a minute.
So this is just a way to visualize it. There's a fixed Earth-Sun line, which is that dashed line that you see across the screen. And so if you leave that line and basically, imagine if you're looking down on top of the solar system, and here's the Earth, here's the sun, and you're rotating around. So if your camera view is rotating with that line, this is what you actually see. And the reason that you get these curly cues is due to the relative eccentricities of the Earth's orbit and the orbit of the spacecraft. So this animation is in the same reference frame. This is from the original trajectory that the spacecraft was sent on in 1928. And here it is orbiting the Earth-Sun Lagrange point, L1. It's about a 6-month orbit, and the reason that they did that was because if you sit a spacecraft at L1, it's really hard to communicate with it because you're pointing your antenna at the sun, and the sun has a lot of radio noise. So they had it in this 6-month halo orbit, and basically the reason that they did this comet mission was because in preparation for the Halley's Comet pass in 1986, the European Space Agency, the Japanese Space Agency, and the Soviet Union all had missions to go near Halley's Comet, and the US didn't, and no one had ever actually visited the comet before. So Robert Farquhar and some other people at NASA decided to take ISEE-3, which had been a solar physics satellite. They first sent it into the Earth's geomagnetic tail. And what they're doing here is a series of lunar flybys. They're actually stealing a little bit of energy each time it passes by the moon. And they did a series of 5 of these flybys. And as you see it, it's going to do one or two more slow passes, and then it will do a very extreme pass where it gets absolutely launched out into heliocentric orbit. And it ended up in an orbit that was about a 355-day orbit. So that's why it took about 33 years for it to catch up back to the Earth. So here you go. And that's animation was done by Mike Lowitz. He did the recent, he and his company did the recent NASA lunar mission Flyby, which was a NASA Ames mission, and it was the lunar atmospheric and dust exploring. Environment Explorer, there you go.
Thank you.
Thanks. They have a lot of experience doing non-traditional orbits. Flyby used some very interesting tricks by virtue of having been launched on a 5-stage solar rocket, which is you don't have a lot of certainty in what orbit you're going to come into a lot of cool things. Anyway, back to Paul.
Thanks, Austin, rocket scientist. All right, so this is another view of the space probe here. It has some interesting attributes. One is that it actually is constantly spinning. It's not like it's fixed in space. It's spin stabilized at this sort of odd revolutions per minute. In addition, you can see here that the thrusters have been shown their positions on the actual space probe. So you've got spin and de-spin thrusters, and the maneuver that we're actually going to do, hopefully quite soon, is to restore the spin speed to this nominal value because it's slightly slow. In addition, you've got these radial thrusters if you want to do some sort of maneuver, like we would like to at some point in the very near future to change its trajectory and put it into hopefully a higher orbit around the Earth. The other cool thing is that you have the antennas here. They are S-band antennas, so we're communicating with it in the 2 GHz region. And then if you look at the total radial length, it's actually 92 meters from tip to tip. So from that respect, you have some really fast moving parts as it spins. It actually has a lot of experiments on board. It's actually jam-packed with them. And so this is part of the approach with trying to get these experiments back up and running and see if we can collect some more data. So you can sort of get a sense of all the different sort of energy, protons, waves, cosmic rays, and so on that it sampled in the past. This is an example of an old telemetry screen, apparently that NASA had to receive telemetry and how they were putting things out. Remember this, because I lost a lot of sleep over the past week recreating our new version, so I'll show you that again. So what happened was, the original mission drew closed, they turned off telemetry, only the transponders were left on, which means there's just a carrier signal coming down from the satellite. NASA decommissioned the ground-based equipment, so what it means is that their deep space network, which is based around the world, Goldstone, Madrid, Canberra, is actually incapable of sending commands to the space probe anymore. The equipment doesn't exist. And documentation has been scattered, and Austin can certainly attest to this, that there is so much documentation spread out everywhere, and it's something that's actually quite contrary to the rig. So we had to do some testing on the fly, but it was, what do you call it, dumpster diving NASA documentation? So the new mission. Our fearless leader is named Dennis Wingo. He's working with Keith Cowie and trying to recapture the space probe. Get some telemetry, fire the thrusters, and bring it into a stable new orbit around the Earth. And then the grand aim is to allow open public access to the remaining scientific capabilities, so using it for STEM studies and so on. So that's actually kind of cool. And this got a little bit of news coverage about NASA signing the agreement with sort of the group in allowing us to communicate with the space probe. So that was a big milestone. So the reason why there's a sense of urgency is because as it draws closer to the Earth, you can see here along the bottom is the date, and then the range in astronomical units as it closes in, and this is obviously where we are now. We have a limited amount of fuel that's left on the space probe, and what this is called is your amount of delta V, so the amount of change you can apply in the trajectory. And so depending on, we have a fixed amount of fuel left, so depending on where it is relative to us, as the days progress, you'll need more and more fuel to try and create the same maneuver. And then obviously once you exhaust this is percentage of delta V capacity, so think about this as the amount of fuel that's required to do the trajectory correction. This is actually old. This is very conservative, so the numbers are better than this. But beyond this date, which is a little bit further out than that, you would need more fuel than is available on the bird. So, Austin, do you want to quickly talk about this one? So this is the success case and the failure case that we will find out.
So, officially, the plan is to go back to L1. That's what we're being supported to do by NASA. That's the current plan. There might be some reasons that going back to the L1 orbit aren't going to be as feasible longer term. Mostly due to cost. You just have to do a lot of maneuvering to stay in that L1 orbit because it's not a stable orbit. Whereas there are orbits around the Earth that are fairly high, or even around the Moon, that we could get into with the amount of fuel that's left in the spacecraft, but don't require this constant maintenance. You have to keep ranging the spacecraft to stay in L1 and then doing maneuvers. I think during the operational mission, they were ranging at several times a week and doing a maneuver like every couple of weeks, just to tweak the path to stay within this boundary, to actually stay in the L1 halo orbit. So anyway, going back to the slide, we're going to be experiencing a flyby of the yeah, there you go. So this is the Moon's orbit, the dark black line. We're going to be experiencing a flyby of the Moon on August 10th of this year.
So watch closely, because if we screw up, there's going to be a bit of an explosion. No, there's not. It'll all be good.
So we basically do what they did in the early 1980s, but in reverse, where we need to do a flyby of the Moon, but instead of stealing energy from the Moon needs to steal some energy from the satellite and reduce its energy to the point where we can capture it into an Earth orbit. And you have to do, obviously, another thruster firing after the initial flyby because due to orbital dynamics. So, anyway, what's that?
So this is if it works?
Yeah, this is if it works, and if it doesn't work, it will basically fly by the Moon. It may actually go into a quasi-stable orbit. We think maybe now. We're getting better and better data all the time. But ultimately, if you don't do a burn, it's not going to stay in the Earth system. It's going to get kicked back out, and it's going to be at least 15 years before it comes back.
Thank you. So, therefore, the mission was born, and they used Rocket Hub to raise funds. This is all crowdfunded. It was a nice little amount they were able to do. So the problem remained that NASA junked all of their equipment, and of course, the only way to communicate with the space shuttle is using RF radio waves. So since it wasn't available, we needed to create a new modulator and demodulator so that the spacecraft would understand commands that we would try and send it, but that we also could understand the telemetry that was coming down, turning it from RF into ones and zeros that we could then parse and display on a screen to actually figure out what state the spacecraft was in. So this is where software-defined radio comes in. It's kind of state of the day. They happened to get in touch with the guy that founded Edis Research, Matt Edis, and they got in touch with John, and then John and I sort of came on board. John, do you want to talk about that first experience with them? So they ended up ordering some receipts from us. This is the network device you plug in over a gigabit Ethernet connection network, and we've got a couple of these at Arecibo, another one on the East Coast. And this is sort of what we have hooked up to GNU Radio and the open source software that we use to communicate with it.
Actually, wait for a
Okay. So we have quite a long distance. These numbers were computed initially at Arecibo. So at the time it was a fair distance away. The spacecraft sending back RF remotely has a 5-watt transmitter, so it needs considerable gain on the dish. There are 2 transponders on the board, transponders A and B, 2 antennas, medium and gain ones. And so basically it comes down to another average link budget, considering we don't have access, NASA doesn't have the capability, we don't have access to their dishes. So one little thing I put together was this little prediction script. JPL, NASA JPL has this horizon service where you can add your observer point, the date, what object you're trying to track and so on, and we'll calculate all of the relevant details. There was some initial analysis by this aerospace company where they detected the carrier about 2008, I think. And so they updated what's called the ephemeris, which defines the orbit. And so that's what we've been working with. But sometime with your dish. So what it looks like then, I'll show you this running in real time afterward, but once it's reading the data and you set what time it was running in real time at the time, it tells you the speed. So the space probe was moving at 3.4 kilometers per second toward this general direction. It was quite a ways away from the Earth at the time. And this is the interesting thing. Usually when you're talking about something on radio and terrestrial communications, you're talking about sending some waves out and getting to the destination immediately. Here, the two-way light time, so this is the time that it would take for us to transmit something, the space probe to act on it, and then modify the telemetry that would be coming back or the signal, would in this case be 103 seconds. So we send something out, switch to receive, and then kind of wait and pray. In addition, there are some frequencies here of the downlink, and because you are traveling very quickly, and the Earth is rotating as well, you have to take into account the Doppler shifts. So if you want to hit the space probe at the right frequency by the time the signal arrives at the space probe, you have to be on the mark. And this little script constantly updates the Doppler shift. So what do you need for long distance communications? Big amplifier and a big ass dish. Here's a picture. Happens to be the world's largest. This is it at Arecibo in Puerto Rico. And we were fortunate enough to be able to go there and set up the initial stuff. So this is from the view of the control center. This is the catwalk. You might remember some films that were actually shot here, some certain scenes. A bit of action happening on the catwalk. And the dome was installed. This is a more recent addition in the life of the dish. And this is actually where all the transmission and reception happens. This is Austin, John and I. Further up, there's a smaller dish. This is looking back down. One of the guys there, Dana Whitlow, is an absolute champ. He's a microwave RF guru. He took us around the Flyby. This is actually on the platform, so on multiple occasions we went up using the cable car or the catwalk, and this is sort of looking down from the dome. It's a bit of a ways down. And they're installing these new ionospheric heaters to do experiments in the atmosphere. This is the view on top of the catwalk. You would get on there and walk across, and to actually access the dome, you walk down these steps, go through the rotary joint here, go down some more steps. I mean, the scale of this is incredible. When you get there, I put my GoPro on my hard hat and walked around, so if you have an hour to spare, you can watch the full uncut deal. But I mean, the scale is just, it's mind-boggling. It's no wonder that you can capture these sort of weak signals, because if you think about it, these are photons, and you think of your umbrella, the more you can capture. So that's Dana, who was taking us on the tour. That's Dennis there. This is actually on the transmitter floor, I believe. This is under that azimuth arm. So that arm that the dome will track across as it tracks an object through the sky. That whole thing is sort of suspended there. So it's pretty amazing the entire thing can be supported by the three columns around the outside. This is actually looking up. Here's the cable car going up. It goes all the way up to the top of the structure there. And this is sort of the bottom looking up into the dome. So they have the secondary and tertiary reflectors in there, and then it gets focused to a point where they position the feed for the transmitter or the receiver. These are those reflectors inside that dome structure. And these are the feeds, the horns that are actually underneath the receiver floor. So you can see that they have these sort of apertures here. This is where the photons get focused. And so they go in there or they're emitted. And it's actually quite a good setup because the focus of the entire dish is always at a fixed point. This entire floor rotates. So back in the control center, they type some commands to select the appropriate receiver or transmitter, and the entire thing turns and positions it exactly where it should be. So it's an amazing setup. It really is incredible. This is in the control center, John and I. They have the operator that sits there with all these screens. It tells you what the current position of the dome is, where the azimuth arm is. They have tie downs, which are these enormous concrete blocks underneath the dish itself that keep the platform level, because depending on the temperature, there's a difference in the tension of the wires. So it's just keep everything calibrated. This is the tie down status here, and weather and tracking information, and this is actually CCTV in the dome. Oh look, there's Austin giving the double thumbs up. One of the guys here is installing electronics. This is actually what the receiver room looks like. So this entire floor rotates. So RFI is a really big deal here. There are signs everywhere to turn your phone off. And amazingly, did they say that the ignition cables on the cars that go in there are actually shielded as well?
They're coax, yeah.
Yeah, they're coax ignition cables, which is pretty crazy. This is what underneath the dome looks like. So you can actually go down a road and if something is hoisted up, which we didn't do, you access it that way. This is Victor, and it looks incredible because there's all this lush vegetation and you've got this sort of incredible curved structure and everything. Actually, one little anecdote here is that we went on a tour with the other guys, Phil, and he said, you know, you have to wear your yellow hard hat all the time. And the funny thing about it is that when you're underneath the dish, you have to wear the hard hat in case like a little nut or a bolt or something falls off the platform, which can happen from time to time. Because if you look at the dish, there are like holes in it, and some of them get patched over. But the thing is, once a nut or a bolt's fallen down and it's already accelerating to that considerable velocity, it doesn't matter whether you have a hard hat on. Phil said basically, if it hits your hard hat, it's going to break your neck and you're going to die. You're not wearing a hard hat, it will just penetrate the skull and you're going to die. So that much like that. So additionally, apart from receiving, it also transmit. So they have this set up for S-band radar. They actually use it as a radar to image asteroids. So here's an example of this sort of image that they can recreate from the returns. And the dish gain, if you think about it, is quite incredible. It's in that value, which is phenomenally huge. And the beam is very, very narrow when it comes out. So this is actually one of the klystrons in the dome. They cool the receivers down to about 35-40 Kelvin, which means that you reduce the noise. They have two 1 megawatt klystrons sitting there that they power combine. And unfortunately, we couldn't use this setup because it was slightly outside the frequency that we need to operate at. But you know, this is some pretty serious equipment. By the time you apply the gain, you're actually outputting 20 terawatts effective radiating power. So it's quite incredible. Now, we didn't see it, unfortunately, we would have loved to, but when birds fly through this beam, apparently, in order, here we go. They're boiled. This is S-band, right? It's like a microwave. They fall onto the dish because they're dead. They catch fire for the enormous amount of energy. And the problem with that is, beyond that, it reflects a lot of the energy back up into the dome, which is bad because the receivers are so incredibly sensitive. Usually there's actually a shutter that closes over the receivers, but still they're very sensitive, so this can be bad. Bad for the receiver back of the bird. Now, so we needed an arrow amplifier, and this amazing hand-built custom amplifiers in Germany, Dirk Fischer, he put together a new amp for us. It does up to 450 watts. And the guys at Arecibo were amazing, and they actually managed to sort of hook it into their existing setup. And we used the existing S-band feed. So this is what it looks like. Who remembers the film Primer? You know, it's that sort of indie film. Don't you reckon that looks like a box? It looks a lot like a box. Anyway, so here it is actually being hoisted up into the dome. So it gets put in this little bucket and gets taken all the way up there. And then they pull it in and set it up. There it goes. So we have about 2.5 hours in each day when we can observe the space probe. This is actually, Arecibo is really busy looking at the schedule and it's jam-packed, so we're fortunate enough for them to allow us on certain days to use that period in the afternoon. The window creeps 2 minutes earlier every day, and because you can only transmit or receive it once, you basically do one in the other and switch back, and it takes a little bit of time to do. So what we've done is we have some USRPs hooked up to their existing RF infrastructure. It's running a new radio here, and you can actually see the space probes carry a signal right there. This is their big patch panel where they have all their RF coming through. You can hook this up in different configurations to do different things. To decode that, you kind of need to decode this schematic. So that was interesting. They have a hydrogen laser as a station reference for timekeeping, which is an incredibly accurate clock. Managed to patch into that. And I'll skip that, but this is one of the flow graphs. This is the very first time we kind of saw the space probe carrier. That was pretty exciting. And we were sort of studying that to figure out what was happening. I'll skip that, but Phil Paralab, who's one of the gurus there, he lives and breathes the station. He's American, he moved there, went surfing, and then he got addicted, and he does this every day. He's an amazing guy. He ran this sort of spider search to try and narrow in and update the ephemera so we knew where we were pointing. And we were happy. It was all good. The bird was there and it was alive, and we had that confirmation because we saw that carrier on our little waterfall there. So this is sort of blown up. This is the very weak carrier on the very first day that we found it. And if you look at the entire spectrum, it's just this incredibly faint red line there. If you do it with the F15 and zoom in, it's just a tiny, tiny little slice of it, just above the noise floor. Once you actually get the pointing right though, it's great because you have this incredible boost in the signal. So this is actually a really strong signal, which is what we expected from our receiver. And so what that's like 40, 50 dB above the noise floor. So that's great, we're really, really happy there. What date was this? This was like, this is the 23rd or something like that?
Yeah, third week of May.
Yeah. And so you can look at that on the waterfall. This is all in GNU Radio, open source DSP SDR framework. If you zoom right in and look at it really, really, really fine spectral resolution, you see how it's sort of moving back and forth? This is actually the Doppler that's induced by the spinning of the space probe. So you can actually determine the spin rate from looking at this carrier alone instead of looking at the telemetry data. So we're there, we had some people filming and stuff, and got a bit of coverage, which was kind of cool. So we received, we want to communicate with it, we want to transmit back out again. So we set up the second USERP, and what happens is this USERP actually transmits the modulated baseband data at an S-band, about 2 gigahertz. And this blew my mind, I didn't realize this sort of stuff existed. The RF output, the analog RF output, goes into this box, and it puts it onto a fiber optic cable. Right? Usually you think about digital modulation and stuff going on fiber optic cable. This is 12 gigahertz of bandwidth going off the single mode fiber all the way up to the dome. So they have all these speeds and stuff going on. And in the dome, it comes back out as RF and then hook up to the amplifier and send it out. So here we're just calibrating some level. This is one of their equipment rooms, and we have it just set up in the rack there. So they were incredibly accommodating. Now, John, you want to talk about this?
So part of the part that we skipped over before is kind of introducing software-defined radio and why it's so cool. I think this project is just a perfect example. At first, the ISEE-3 Reboot project, they kind of went to some of the experts at NASA and said, hey, there's this opportunity coming up to do this maneuver. Can you help us? Can you help us get that communications equipment, or can you help us recreate it? And the answer that came out was no, it costs millions of dollars and it would be very difficult. But they came to this research. It was exciting for me because I'm all about aerospace. I love it. And I looked at it, and it just seemed like a little bit of a... Yes? It looked like a slam dunk. And that's not because I'm super smart or I really know this stuff. It's that,
he does.
Software-defined radio, Edis Research, GNU Radio, it's kind of developed this ecosystem, this community around it, so that stuff like this actually takes a half a day, and that's literally how long this took. So all this neat stuff that's in the straight line and kind of organized over here, that's my part. I could kind of talk through the details of how that works, but it's some interesting modulation where it has multiple data and carriers, so the receiver on the spacecraft can be super simple and not have to recover the clock. And then all the stuff over here, I just pick on Bob. That's his stuff where all the blocks are kind of mashed together. But essentially, I'll have a pointer. Effectively what happens is, how does this work here? Well, anyway, you start at the left side, and there's a socket interface that takes some data from the application that sends the commands, and it goes through these mathematical processes that's built up graphically here, or you do in Python, and it comes out as an RF signal out of this USRP device that we've talked about. And you know, this is kind of, once you put all the bits through and you do all the math, this is what it looks like in the frequency domain. You know, it's pretty non-standard modulation that you wouldn't see too often. But the other part of this, as Balint and Austin alluded to, is there were just hundreds of documents from NASA talking about how the space probe worked, how long, or how the link worked as well. And it's amazing how many of them said something completely contradictory and different. So there are a lot of ambiguities and only small contact windows at Arecibo to try it. So what we did is we did kind of an automated script where we looked at all the different possibilities of how the modulation was put together, and we kind of tried everything. And then we stepped across a wide frequency range in case there was an offset on the spacecraft itself. And it turned out pretty well. It was super exciting, and we sent those commands up, and we actually saw a response. You know, it's been well over a decade since anyone had talked to the spacecraft, well over a decade since those circuits had been stimulated. So that was pretty awesome. Oh, and then you can guess whose photograph that is.
Apparently.
I'm going to let him talk about that.
Thanks. So John made this amazing script that suite, and we've been using that every day, just to verify then that it was transmitting the right stuff out, because of course we want everything to work. I put this together, which is sort of the equivalent of the spacecraft's receiver. So this is what the spacecraft was to kind of see as we send up commands. This is in frequency domain. This is looking at it because it's phase modulated. It has various components to it that sort of give you clock and data. And this was just looking that you've got the right bits coming up that were originally sent up. The telemetry is really interesting because it's convolutionally encoded, which means that because it's coming across an incredible distance, it can be very weak, and there are potential for errors to be in your data stream. And those ones and zeros can be flipped, and of course then you might have data that's corrupt once you actually receive it on the ground. It's actually using this thing called convolutional code, but it has this neat property that you can skip the really, really expensive decoding and look at it quickly. And that's the original paper. This was when we were doing the uplink. And this was kind of cool here, because this is spitting out the offsets that it was trying to send a command at. So as John was saying, it was trying all different combinations. But to make sure that the signal was actually getting out of the dish and going up to the spacecraft, because as we found out, there are lots of other things that can go wrong. This is another little software-defined radio that I have here with just an antenna. So I've just got it receiving there, listening to the things coming out of the dish. And what do you know? The modulated command is appearing there. So it's a confirmation that everything is working, which is good. This is the moment where we actually sent the command and the telemetry was turned back on. So instead of having that little lonely carrier, we saw these side bands come up. And it was an amazing moment. Woo! That remains to be shared with all the guys, because there's a huge amount of research that went into it. So we celebrated. John unfortunately couldn't make it, so we joined together using, what's that? Not FaceTime. What's that thing called? Hangout. So we're hanging out. And Nick Biscuit Foster, where is he? There he is, Nick. Another total SDR guru down there. He managed to join them too. So it was a good time. So that's what it looks like instead of being that little line, what it looks like when it's actually modulated. So there's actually one thing that's really floating over there. So that. So we managed to transmit to transponder A and turn it back on B, because one can control the other. And then, so this is actually telemetry coming down on both. We had two radios receiving simultaneously. This was the new radio flow graph that's used to actually decode that telemetry circuit. It tracks the carrier, and then it phasely modulates it, so you have your zeros and ones there, and you have your raw binary data stream in there. You can slice that, you can check that the rate at which it's coming down is what you expect, and then you find the synchronization point within a frame of data. The legend Phil Kahn actually contributed to the project by writing this amazing Viterbi decoder, and he claims the world record for the longest constraint length, which is pretty cool. So this was received telemetry. His decoder would decode it. Boston would have a look at the ones and zeros, and then we actually determined some of the things on the spacecraft, and this is pretty good. With the ranging and filled in, and we're finding ephemeris, so we know better where it is. And now we actually, we're back and have this set up and remote into our receiver with a laptop that connected to yourself, so you can see what's going on. So this is actually back at the office here. So this is Jacob Gold, another member of the Reboot team, and this is my colleague Ian, who happens to be over there. Thanks for all of your help and advice on doing the sounding board. This is actually, remember how we had those beautiful plots at the FFT? This is actually the ASCII art version, because we had internet connection issues, so we're making sure that you can see it with ASCII art. Now, one of the things about the spacecraft is that this is coherent ranging mode, so you can turn it on and then it'll actually track the uplink carrier by moving the downlink carrier at a particular ratio. And then when you send it stuff, it'll act like a bent pipe or an RF megaphone. So whatever it's sent, whatever you send it will actually repeat to you. And this is a good way of making sure it works and figuring out exactly what it is. So we've been doing a bit of that as well. So this is, again, this is a waterfall. And this is the sort of normal rest frequency of the thing. And we send it some commands, and you can see that it starts tracking our carrier. Because we sent commands at various frequencies, slowly stepping up. And here you can see that it's actually following that step sequence. So this is really cool, because it also means that many other parts of the receiver and transmitter are working with the spacecraft. Here it is again. This is actually, was this today?
Yeah, that was today.
This is today. So this is kind of cool because it loses lock and then it gets it back again as we continue stepping the commands up. That's the annotated version, just with all of the different steps that we went through and how it's tracking. And this is really important because you can use this to look at the step size and actually derive the Doppler shift from this. There's a bit of maths involved, but then you compare the derived Doppler from this against what NASA says, and you find it's actually a bit off. So we need to fix that. And this is another GNU radio app that can send out these codes and attempt to do the ranking. We haven't been able to try this yet because we need to write some of the code, but that's the process. Alright, so this is the telemetry screen. I've had a couple of sleepless all-nighters lately, but these are the sort of frames that you get as the telemetry screen comes down. So it's a whole bunch of 1s and 0s, and there are 128 bytes in this minor frame, and it cycles through 256 of these minor frames to make a major frame that describes everything about the spacecraft. There are also additional subframes in that, analog subframes and digital subframes that are 64 length, and these are slowly built up as you go through each of the different minor frames. This is actually the new telemetry screen now, so you have all this information about thrusters and firing ratios and so on. When we want to do the maneuver, we check that the row bits come up here, whether certain valves are open, what the tank pressures are, and so on. And I had an all-nighter and I was pretty tired after that, so I was just hanging out. So that's, who recognizes that?
It's a bird, right?
No, it's not contact. GoldenEye, yes. So we don't want to upload the transmitter. So just to finish up very, very quickly, I have a live demo. If you'll indulge me just for a second. So whenever we hook up at our receiver, we record everything. So this is actually a recording playing back with the telemetry coming down. So I'm just going to show you. So you can see here, this is locked onto the carrier, and then I'm going to run the telemetry decoder, and you can see that running here. So it's waiting for the sync, and then it gets the sync, and then it updates all the bytes in that major frame, and you can see it scanning through. You want to have a look at the subcom frames that they're built up, it looks like this. So this is as it goes through each minor frame, it builds up each byte in the subcom frame. And then if you want to look at like the command counters and so on, you can see them up there. And the very top one is the current index of the minor frame, so I'll keep going up. And then if you want to look at the thruster dial, I don't have enough lines in this screen, so it crashes. But it looks like that screen before when you get all the information about the various thrusters and selectors and so on. Just one other thing I wanted to show you here. If you wanted to know what the spacecraft is actually doing right now, then we can bring up that script I was telling you about. So it's currently, what's that, 8.3 million kilometers away, moving at 2.5 kilometers per second. And they're the current frequencies that we would need to target to talk to it. And the last thing I wanted to show you was, when you run the telemetry, you know how in a lot of those space documentaries they show the CG rendering of the space probe, and they have this sort of little audio track running next to it as if it was sonifying the data. Sorry. Audio. No, it's not working, sorry. Maybe I can show you later if you want to talk. But yeah, that's the general gist. I know we've got a little bit over time, so I guess any quick questions for any of us?
Yeah. What exactly are you waiting for before doing the thruster burns?
If you can,
as you said earlier,
repeat the question, should we?
So the question was, what are we waiting for before we do the thruster burns? Was that about side?
Yeah.
Well, actually, the thing so far has just been completing the real-time telemetry. So I did an all-nighter on, what was it, Monday? And then we sort of did a test on Tuesday. There were specific commands that we wanted to send to turn on the attitude control system, and just making sure that the sort of initial steps leading up to that, the spacecraft would execute those correctly, and we would see what we expect to see on the telemetry. Do you recommend?
Yeah, so we actually need to get permission from NASA because of the way they still own the spacecraft. We currently have permission to do the spin-up maneuver, and we've done work in that regard, and we're getting very close, but we're trying to be methodical, and as things come up that we didn't expect, that's kind of been the story of the last couple days, where, Anyway, we should be on track to do it. We'd like to do it by about July 3rd. Because we've been able to adjust the ephemeris due to the tracking taken on Arecibo, this situation is much better than we thought it was a couple months ago. So we're not going to be using a substantial portion of the fuel if we can do it by sometime in the first half of July or so. We should be all right.
Okay, got the audio for you really quickly. You hear that? So actually in the documentaries it does sound very similar. So this is actually the ones and zeros coming back from the spacecraft that eventually get decoded. So it's kind of pretty cool. You see it in one respect, but you can also hear it in another one. Any other questions?
So you're tracking your only communication is Arecibo, but originally I assume it was tracked from more than one location, or was Arecibo the location in the original?
They actually, yeah. So the question was, we were only tracking from Arecibo. Obviously, there were other tracking stations that were doing this when the satellite was operational. They actually did use Arecibo in 1985 during the Comet encounter, just because of how far away it was. They needed a dish the size of Arecibo to communicate with it. But NASA runs the Deep Space Network. They have, which Paul mentioned in his presentation, they have 3 major facilities: Southern California, Madrid, and Canberra. And they don't have the equipment to talk to it, but they have allowed us to attempt to use their facilities for ranging to the spacecraft. One of the things that's required is that they actually have to send a couple of commands to get it into the right mode for ranging. And if you don't start ranging immediately, it kicks you out of that mode. So, which was not in, it was like a footnote in one document buried somewhere. So we had to pre-record some commands. They're going to send those up. We're getting that all worked out right now.
There's another question over here.
Another question over here.
Yeah, you raise your hand.
No, that's right. Well, the bit rate, the question is what are the bit rates? They're configurable. We can go from 2K down to 16, depending on distances and quantities are.
This seems kind of like a long shot at the beginning. What made you think it was really going to work?
The question was, it's a long shot. What made us let it work? I guess. I mean, John and I were brought on later, but also.
So at the beginning, I didn't really think it was going to work. We decided to just learn as much as we could about the spacecraft, and it wasn't really until these guys came on board that I went, oh yeah, software-defined radio, that makes sense used to this. But before that, I figured we'd be soldering up a bunch of stuff and it wouldn't work. I mean, I've built a lot of hardware in the past, and there's teething problems and things get expensive, and the software-defined radio has really been incredibly good.
Not soon. We're just waiting to get in the right orbit and so on. The question was, are we going to access the instruments anytime soon? We just, I think we're holding off on that until we're satisfied with it. Okay, all right. Just final thing to wrap up. I'll let this go. This is the happy dance when we realised that it was all good. I was sort of checking the wire, making sure everything was all right, because there's that moment of disbelief. Phil now sees it on the scope. Really happy.
I haven't run the numbers, but I think that's incredibly unlikely. It's only about 1.6 meters on a 1.6 by 1.6 meters. It would be thinking about it now. It's going to be pretty far away. I don't think that's going to happen.
Well, 2 more questions while we set up our next meeting.
I'm sorry?
How does this probe know that you're allowed to do this thing?
There is a procedure which, oh, sorry. The question was how does the probe verify that you are authorized to use commands? And I don't think I'm really allowed to speak to that.
No. How is the validation of the bits they're sending to
Actually, yeah. So it has solar. It had a battery. The battery failed by 1981. So it's been purely on solar. And the degradation on the solar cells has actually been much better than the models would have suggested. We're getting about 146 watts right now. The useful life power was 170 something.
Will it die in the shadow, or is that?
So yeah. That's the question was, will it die in shadow? And that is a really interesting thing. Because we're going to have to do, when we do Lunar Flyby, it's going to go into the shadow of the moon, it's going to go into eclipse. And that's a problem because everything dies on the spacecraft. It will come back up once it's powered. But because the structures are hydrogen monoprop, it can freeze. And if it freezes, you can have problems with it breaking things because it doesn't expand like water does, it contracts. But you can end up having things kind of freeze in one direction and thaw in the other direction and get pressures that will break things, and they did this in testing. So there's a procedure. They had to do this in 1982 after the battery had died, go through eclipse. So there's a procedure that involves getting everything really hot beforehand, and then you go through the shadow, and you're in shadow for about 20 minutes, and you just try to radiate. Not enough heat to allow things to start freezing and causing problems.
that about it.
Sorry for